Okay. All right. Thanks, everyone, for coming to DA week. I'm happy to lead it off, and I'll talk about coupled data assimilation and CESM, but I've also dedicated a fair amount of the presentation to just providing some theory background for data assimilation in ocean and coupled models. And so I'll talk a little bit about why we care, why it's important and interesting to think about doing data assimilation in this context, to provide some background on the machinery, talk specifically about data assimilation efforts in CESM, and then talk about some of the big open questions that I think we have to look forward to in the coming years. So first point of motivation for doing data assimilation is that the ocean is only sparsely observed. Even in the last 10 years in the Argo and the altimeter era, we don't have a complete picture of the ocean from observations. And so it behooves us to introduce information, dynamical information that comes from models. So this is a figure from a recent paper by Laura Jackson and co-authors that compared 10 different ocean reanalyses, pictured here, to examine properties of the North Atlantic. And I'm showing here the barotropic stream function strength in sphere drops of time mean from 1993 to 2010. The point I want to make here is that these models were actually all very different. They had varying degrees of resolution from 1 degree to 1/12 of a degree. So these barotropic stream functions look quite different. But one of the takeaways from this paper was that as time moves forward and we accumulate more observations in the North Atlantic Ocean, there seemed to be a kind of collapsing of various emergent properties of these various models. For instance, AMOC strength and Labrador Sea mixed layer depth, which you see on the right here. Can people see my mouse?
No. Oh.
Is that a no? Okay.
Yeah, I can't see it.
I'll just be demonstrative. So this just points to the potential for data constraints to kind of deliver similar performance in models that are themselves very different. A second motivation for ocean state estimation or data assimilation is initialized prediction. And here I'm showing a figure from work on the decadal large prediction ensemble, decadal predictive large, DPLE, which is showing a difference in forecast skill for upper ocean heat content between the CESM large ensemble, which is just forced by boundary conditions, but not initialized to a particular state, and the DPLE, which is both forced and initialized. And the takeaway here is that when it comes to decadal prediction, at least in CESM, and certainly in some regions, where you start matters. The initial condition for predictability seems to be important. And so then in the case of real-world predictability that we want to study, it's important to try to arrive at an ocean state that is close to observations. And so this raises these interesting questions of how we can improve predictability with data assimilation, and also what the limits of predictability could be for different components of the Earth system. Data assimilation also provides us with a suite of tools that can provide dynamical insights that are complementary to those that you get from forward models. So this is an example of something from the weather world, the ensemble sensitivity of the longitude of a tropical cyclone at a particular time lag 2 days in advance to wind strengths. And that's the picture that you're showing here. Basically, this is where you want to blow the wind if you want to change the course of Hurricane Katrina. And I guess this has promise in the climate world. If we could use tools like this to study longer-term climate variations, the NAO, how mechanisms leading up to that, that's a potentially powerful tool. And finally, and something that I'm really interested in, as we move to longer and longer climate time scales, the data only become more and more sparse. Which means that if you can hack it, data assimilation really becomes more and more important as we're going out to these longer timescales. So I'm showing here 2 reconstructions of sea surface temperatures from deep time paleoclimate, the Pliocene, and then the LGM, slightly shallower time. And so these are data assimilative products trying to get at SSTs that are being used now in the study of equilibrium climate sensitivity. So really, pointing towards the use of data assimilation for climate variability on long timescales. So that's, I think, some of the interesting motivation for why we're doing this. And now I'll just provide a little bit of background on the machinery that hopefully will inform the next two talks that we'll see as well. And data assimilation techniques can be roughly broken down into two different categories of techniques, sequential methods and variational methods. And I'll just give each of them a brief summary here. So sequential methods, and I'll talk specifically about ensemble sequential data assimilation. They're called sequential because as we're moving forward in time, you're going to make changes to the climate state in order to fit observations. And so by the state here, I mean a list of all the prognostic variables that you have in your model. So for the ocean, temperature, salinity, and velocities, that kind of thing. So the procedure is starting from a particular time to integrate an ensemble of models forward in time until you encounter an observation of some quantity. And to assimilate that observation, what is done is to then sample the models like the data. So if you have an observation from the North Atlantic, you'd look at North Atlantic temperatures, for instance, and then to compare the models and observation, and then add increments to the model states that improve the fit to the data. And then having added these increments, you have a new set of initial conditions, and you can continue your integration. And integrated over some period of time, what you end up with is a reanalysis or a trajectory of an ensemble of model states that reflects the model physics and also these adjustments that you get from fitting observations. And just to point out that there's some challenges and shortcomings in procedures like this. The first is that when we come across an observation, we're really just changing the model state kind of by fiat. And this can lead to some funny things. If I have an observation of a temperature that's incorrect in the deep ocean, I'm just kind of introducing a temperature change. And so what can happen is that you break the model physics. And also by virtue of these ensemble approaches, there's two tools that I'll mention briefly that are often necessary called localization and inflation. Localization is necessary because in ensemble data assimilation, we're often limited by the number of model ensemble members that we can run because it's expensive to run these models. Why this matters is that as we accumulate more and more ensemble members, the regression patterns that we have to make our increments become less accurate. So this is a sort of classic example. This is a pressure field, correlation with a pressure field anomaly. So this is in the atmosphere. And in the top panel, you'll see this correlation computed with 32 ensemble members, and in the bottom panel with 128. These regression patterns are important because they tell us if we have an observation, for instance, off the coast of North America, where should I change the model state? So what we see is that as we reduce the number of ensemble members, we get these spurious correlations that just come because we don't have a high enough n to estimate these regressions correctly. And so a typical procedure to do this, noting the fact that these smaller covariances are often at greater distances, is to use what's called localization, which establishes typically an isotropic radius inside of which these correlations are attenuated and outside of which they're set to 0. So I think of this as kind of a pruning exercise where you're kind of getting rid of the things that you trust least from the ensemble. The second approach that's often necessary is called inflation. And this arises because when we make these increments, how much the state is changed, the size of the increments, depends on the spread of the ensemble members compared to the observational uncertainty. And this makes some intuitive sense. If you were to say have 3 ensemble members that were all doing very different things in the ocean, and then along comes an observation that you really trust a lot, you would hope that you would be able to correct your each of your ensemble members in kind of a big way, a larger increment. Whereas by contrast, if your ensemble members are really telling you, the model really knows what's going on, and you have an observation that's very uncertain, then the changes to the model trajectory are going to be relatively small. But this is a problem because ensemble sampling often will systematically undersample some types of the model spread. Just for instance, often you're using the same model, and so there will be model errors that are in common among ensemble members, so you're not sampling that error. And in the course of a sequential filter step, this sort of, the model ensemble members can get closer and closer together, and this leads to filter divergence, which is basically that you're totally ignoring the observations, which is not something that you want. And so inflation is sort of a commonly prescribed treatment. It's not necessarily a solution, where you're basically just spreading out the variability of the ensemble members, and this can either be additive or multiplicative. So that's kind of a quick background on the sequential methods, and then just for completeness and hopefully to provide some background, especially for Travis, I'll talk briefly about variational approaches. So in sequential methods, we're advancing a model forward and making corrections at all these times to get closer to observations. Variational methods have a bit different approach mathematically, where they solve an optimization problem to minimize an objective function. And I'll just illustrate this using an example. The echo state estimate is an example of a variational method. And so, excuse me, in the echo state estimate, instead of adding changes to the state vector at each time, they define instead a set of control variables. So this is atmospheric boundary conditions and the initial conditions in the ocean, and also in some of the parameterized physics. And what echo does is say, well, we're not going to change the state, the temperature, and salinity of the model, but instead we're going to change these control variables. And specifically, you change the control variables to solve an optimization problem. The solution of control variables is given by the set of time-varying controls that minimizes an objective function with two terms. Basically, you want the model to fit the data, but you don't want the control adjustments to be too big. So you don't want the wind stress to have to be 10 times its climatological size. And so this variational approach, this is an example of 4D var because it's computed over the time history of observations. It's 3D var if it's just done one time at a time. There's some advantages and disadvantages. I think the big advantage is that unlike before where you're adding these increments and maybe not conserving ocean properties, here you are. You can make budgets that conserve heat and salt. Moreover, the 4D var is a smoother, not a filter, which means that information from observations, rather than just making a single increment at the time when you have an observation, that observation is also going to affect everything that happened before that observation came along. So information is flowing both forwards and backwards. The disadvantages are that you can generate spurious fluxes. You can fit the observations for the wrong reasons. And so, for instance, in that discussion of North Atlantic reanalyses, they point to the fact that echo has some spurious fluxes in the Labrador Sea. Ensemble methods have the advantage of having these covariances that are state dependent, so that how an observation affects the state depends on the state itself. And 4D var methods use these climatological covariances, so that's kind of a downside. But Travis might talk about some approaches that kind of have a hybrid between the two. Finally, there's no uncertainty quantification. And then the reason I think that a lot of people don't do this is that it's expensive to run and to maintain, and the adjoint of the model, which is necessary to run 4D var. Okay, so having gone through some of the theory background, now I'll talk about some of the applications of DA that have been done in CESM. So one of the earliest applications was the assimilation into an ocean-only model, POP2, 1 degree, by Alicia Karspek and authors in 2013. So here they were assimilating subsurface temperature and salinity from the World Ocean Database in an 8-year simulation using 48 ensemble members, in this case forced by individual members of a CAM4 atmospheric reanalysis. So a lot of the spread among the ocean members in this case was actually attributed to these the forcing that you get from different atmospheric ensemble members. And some of the things that they point out are big challenges that will persist through the rest of this talk. One of them is these biases in Western boundary currents in the model. And this is kind of illustrated by this panel on the right. On the top, you see the model data SST misfit before data assimilation. So this is just kind of running the model and letting it do its own thing. And they identify these 2 points where this model data misfit is particularly high, the X and the cross. And then afterwards, after doing data assimilation on these in situ observations, the changes that are wrought by the data assimilation are insufficient to really get rid of this model data misfit. And this is attributed in part to the fact that it's just hard to tug this boundary condition where you would like it, this boundary current where you would like it to go. And that's probably in part because it's a low resolution model that has a low resolution representation of boundary currents. And a second thing that was noted was that there was a very small ensemble spread in the deep ocean. And as we discussed earlier, a small ensemble spread is a problem because then the data assimilation is just going to say, well, that has to be it. All of your models are saying that that's basically the truth. So that it makes it difficult to assimilate observations. And this could be attributed in part to the fact of how this ensemble spread was generated, mostly from the top of the ocean column by these different atmospheric reanalyses. So one of the things that Karspechdal pointed to was the possibility of using inflation to address both of these problems, the boundary currents and the deep ocean. But it wasn't clear that that was necessarily going to do it alone. A second application published a couple of years ago was now in a weakly coupled framework. And so by weakly coupled, I mean that this is a active, CESM with active ocean, atmosphere, land, and sea ice, 30-member ensembles. And the data assimilation is happening now not just in the ocean, but also in the atmosphere. And so this is illustrated in a prototype 12-year simulation. And it's weakly coupled in the sense that when observations are assimilated into the ocean observations affect the ocean, atmosphere observations affect the atmosphere, but there's no interplay between the two. And we'll talk about this a little more later on. And so, in moving now to coupled data assimilation, the authors identified some good things and again some challenges. The first was just the cost of running a large ensemble. Running 30 members of fully coupled CESM1 was very expensive. And there were also issues at the time with the flavor of data assimilation. So this is using DART, the Data Assimilation Research Test Bed. At the time, it had issues with memory redistribution. And there are problems that persist to this day, originating from the cost of restarting CESM after every model assimilation step. Looking at the sort of output of the simulation, again, we have a kind of comparison of the model SST misfit before and after data assimilation. And so one of the things these authors pointed to was that the data assimilation can reduce the model data bias where there are data, for instance, in the Western boundary current or the North Atlantic regions, but actually saw some increases in the model data misfit elsewhere in the regime that were not data constrained. I'll talk briefly also about some work that Fred Castruccio has been leading, submitted now, addressing both the difficulties in the boundary currents and the low resolution model, and also the quite high cost of running these ensemble data simulations. So Fred has run high resolution POP2 in I think it's 84 member ensembles, and assimilating satellite and in situ ocean observations over a 6-year period. 84. But what's different about this approach is rather than using an ensemble filter, as I described earlier, where you have a large number of simulations running in parallel, this work is using what's called ensemble optimal interpolation, which is going to reduce the number of simulations to 1. And then when an observation comes along, instead of having a range of different ensemble model realizations to look at, you make perturbations that approximate the forecast errors. So the big upside of this is that you have a factor, in this case, at 84 reduction in cost, which is allowing you to do data assimilation at 0.1 degree pop. The downside is that, again, you don't have these kind of errors of the day. The covariance error statistics that you have are stationary, and you might be losing some accuracy as a result of that. So now I'll get to work that's kind of ongoing and more forward-looking regarding specifically the coupled CESM2 and Dart. So work has been going on, and credit especially to Ben Johnson in the Dart group for updating scripts and running some of these test cases. Work has been going on to couple now CESM2 with the new version of the Data Assimilation Research Testbed, Manhattan. This will hopefully deal with some of the memory issues that we were having before, gives us new tools for strongly coupled data assimilation, which I'll talk about, and also for adaptive inflation, so inflation as a function of space. And so these are just some very early results of now POP2 ocean-only data assimilation forced by 80 Ensemble members of now a CAM6 reanalysis that's being run by Kevin Rader. And so I'm just showing here data assimilation increments. These are changes to surface ocean quantities on day 5 of a very short simulation. But this is just to give you a feel of how the ocean state is changed in places where we have observations. And the length scales that you see here will reflect both where we have observations and the localization length scales. So the goals for this moving forward with this CESM2 Dart configuration, one of them is to investigate, as mentioned before, DA ensemble initialization for some case studies of particular interest. For instance, this cold blob in 2015 that's been studied by Liz Maroon, Steve Yeagers, and others, and to try to start addressing some of these questions of predictability in data assimilation. Another project is to perform analyses of these data assimilation increments that I'm showing here. Part of this is if you can predict data assimilation increments. So that is to say, if the model has a persistent bias or deviation from observations, it's possible to incorporate these into the model tendencies or to use them to improve existing parameterizations and develop new ones. And so this is part of a project with the Schmidt Vestre Foundation that I know some folks at GFDL are involved with too. And so then the development goals in the near term are to move from ocean-only DA to weakly coupled DA with CESM2 and Dart Manhattan. And then looking ahead, as MOM6 comes online and CESM, we'll certainly, we're going to incorporate that. In the meantime, we expect a lot of challenges to be in common between POP and MOM, just regarding how we're going to do coupled DA. Okay, so in the remaining minutes, I'll talk briefly about some sort of bigger picture challenges and opportunities for coupled climate DA that hopefully we could include in the conversation later. So one question I have is, I showed these results earlier where there might be a sort of convergence of data assimilative models when we have lots of observations during the Argo era of some properties, for instance, in the Labrador Sea. The question, though, is how long do we have to wait in order to accurately describe decadal and longer period climate variability in assimilative models? Do we have to wait for 50 years of Argo in order to look at 50-year variability in the ocean and the coupled climate system? My hope is not, but I think it's an interesting question. And there's some insights into this that have been provided by idealized data assimilation studies. I'm showing here a couple of results from this paper by Tardif and Hakem, where they coupled a Lorentz model to a Stommel box ocean model, and then reported correlation of what they called the AMOC in this very simple model to a series of simplified atmospheric properties that were resulting from this chaotic atmospheric model. One of the things that they point out in this simple model is that the relationships between the fast and slow components, the atmosphere and the ocean components, are stronger when you compute longer time average durations. So it may be that while it's difficult to constrain the instantaneous or yearly average values of AMOC or these other like large-scale climate properties, that these longer period averages, if you can constrain them with DA, might be lower hanging fruit. Another point is that the ocean integrates the time history of atmospheric forcings. And so when we make these sort of incremental adjustments to the ocean state at the moment when we have an observation, we're kind of leaving behind some information on the table. And so this is illustrated by this figure of adjoint sensitivities of AMOC strength from a study by Helen Pillar and co-authors. So here they said, how can we change the freshwater flux and the Atlantic Ocean in order to change AMOC strength at 26 north? And so when you look at a lag of 1 month, there's a very clear signal about the array, quote unquote, at 26 north. But there's actually a strong signal that persists for 15 years back. So I think this begs the question of whether, for instance, when Alicia Karsbeck and co-authors were finding that the spread in the deep ocean was too small, this might reflect the fact that low frequency atmospheric variability that they were forcing their model with was too low. It also begs the question of whether it could be possible to implement a smoother, a Kalman smoother, to incorporate some of these longer term influences backwards in time from observations. And then another major avenue moving forward is the possibility of doing strong coupling, a strongly coupled data assimilation. And I mentioned briefly before the definition of weakly coupled data assimilation, which is where effectively you have an ocean model coupled to an atmosphere model. You perform data assimilation separately in those two domains. And then the sort of only crosstalk that you get between ocean observations and the atmosphere comes from the model coupling. Strongly coupled, by contrast, has these cross-component covariances such that the atmosphere can affect the ocean and vice versa. And there's some early indications that this could be important in increasing the accuracy of these reanalyses. These are some results by Travis Sluka, who will speak next, or actually last. And the blue regions in this map on the right-hand side show places where strong coupling improves a perfect model analysis for upper ocean temperature. And the red show places where it disimproves it. I guess the questions moving forward are, how important is this strong coupling for initialization and state estimation? And it's an important question in part because a lot of the mechanics of how to perform strongly coupled state estimation remain unclear. For instance, this question of localization was fairly straightforward when you expressed it geographically in space, but it becomes more complicated when you think about how to localize vertically across a fluid interface between the ocean and atmosphere. OK, so looking at time, I think I'll just leave my conclusions here and then take any questions. Thank you.
Thanks, Dan. Questions for Dan? Get my chat box up here. Bob.
Thanks, Dan. That was a very nice overview of data assimilation. One of the challenges that I foresee going from, say, POP to MOM6 is that in some ways the MOM6 algorithms are formally less linear than the POP algorithms. In other words, tracer transport, for instance, involves a correlation with thicknesses and other things. In the context of data assimilation, are there formal assumptions of linearity that we are going to need to be aware of as we move to using a more nonlinear model? Or put slightly differently, how do you deal with physical limits? For instance, we know that a salinity should never be below 0, but when you're doing kind of a quasi-linear assumption and projecting through correlations, you could easily imagine something where it would say, well, the best correlated salinity is negative.
Yeah, those are great questions. And yeah, some of the, I guess, first thing I would say is that these models are already nonlinear, and there's nothing that's saying that we're assuming about linearity in order to make these methods work. Specifically with regarding the tracers, I would be interested to see, and there are approaches I think that could that you could take, maybe changing the frequency with which you're assimilating observations, that might try to get at some of those issues. But yeah, that's a good question. I can't say if there could be problems regarding the way that the tracers are handled. Regarding other, there are other physical quantities that have these hard limits that don't obey Gaussian statistics, and there are tools for dealing with those as well. So if necessary, I think some of those could be brought to bear on the problem.
Any other questions for Dan at this point? And we can come back to Dan at the end, and as well as have a more general discussion. Okay, I would just quick question, Dan. Maybe it's not a quick question. What maybe in the context of this comparison of reanalyses you've seen, what are the most serious gaps in the current observing system that are, precluding additional convergence between the reanalyses, or would lead to the degradation of the reanalyses? What if we were to invest more in the observing system? What would be the most advantageous investment from a data assimilation reanalysis perspective?
Well, that is a question that data assimilation can answer, and there is a literature using data assimilation to do these sort of formal network designs. It does depend on the question that you're trying to address.
Sure.
Some easy ones I think are the deep ocean is quite underobserved, and so something like Deep Argo, especially if you're interested in biogeochemical DA or something like that, holds a lot of promise. But well, yeah, specifically, I guess it'd say it's problem dependent. But that is one of the things you can study is to do these sort of network designs.
Okay.
I don't have an easy answer for you.
No, that's useful. Thanks.